So now we're going to do some example problems from section 2.6. Okay, so finding vertical and horizontal asymptotes. So basically what you need to do if it's not factored is factor the function, because that can help you figure out what is going on. Now, when you're factoring, don't forget if there's a common factor, in this case next, you can pull it out, so we get x times x minus 4. And here we get x squared minus 4, which factors out to x plus 2 times x minus 2. Now, vertical and horizontal asymptotes. So there are a couple of vertical asymptotes. There are none in common, right? The vertical asymptotes would be at -2 and 2. The horizontal asymptotes require you to look at the power, the degree, which in this case they're both the same. And if you took the limit as it tended towards infinity, infinity squared over infinity squared would simplify to 1. So that would be the horizontal asymptote, and you would be done. Now, obviously, you can see that the zeros would be at 0 and positive 4. There are no removable discontinuities. It is discontinuous at 2 and -2. And the end behavior would be x tends towards positive or negative infinity, y tends towards 1. All right. Find any asymptotes and holes in the graph. Now, this is where things get fun. Rewrite it in standard polynomial form. Don't forget that's a +3. Same thing here, except there's no +3. Oh, I'm sorry, there actually is. And then factor. I like pulling a negative out because that makes my life, as far as I'm concerned, easier. I'm just going to take a little leap of faith here and assume that this can be factored. Which means that way I'm actually going to try something. Now, the denominator is not too terrible, 2x and x, right? So 2 times what plus something equal multiply, adds to get 7, but multiplies to get 3. And if you do 2 times 3, because the only factors are 3 and 1, that's a 6 as long as it's positive, and then plus a 1, so that would be the factorization of the denominator. Pulling out the negative does come along for the ride. It's not going to affect anything, but it does mean we have a 5x and x. The only way to get 5x squared would be with 5x and an x. The only way we get a 3 is with a 1 and a 3. Now, 1 has to be positive, 1 has to be negative. But if you take a look, 5 times 3, if it's positive, gets you positive 15, minus 1 gets you a positive 14. So, finding asymptotes and holes in the graph. The reason I had to factor the numerator and denominator is because you'll notice this would be a removable discontinuity. So we have a removable discontinuity at x equals -3. And if it's a removable discontinuity, then it is not an asymptote, which is at -1/2. Remember, you're looking when is 2x plus 1 equal to 0. So you subtract 1, divide by 2, x equals -1/2, which is how we get the vertical asymptote. Okay? And that's actually all we've been asked to do for that. We could find the 0 if we wanted. That's 1/5. Looking at this is a -5/2 because they're the same. The vertical asymptote, the horizontal asymptote would be -5/2. Okay. All right. Find the domain of the function, which means we need to look at or concentrate on the 3x cubed plus 24 and see, is it ever equal to 0? Well, it's 3x cubed, x cubed equals -24, divided by 3, x cubed equals -8. Now remember, it is possible to take the cube root of a negative number and you get a negative number, so it turns out to be -2. Now, just to be safe, I know that -2 seems to be a factor, so I'm going to see if I get something else that's factorable. So I'm using synthetic division to... Now, first off, the remainder 0 tells me that I'm looking at 3x squared minus 6x plus 12, which I can pull 3 out of. Right? Now, unfortunately, if I do b squared minus 4 times a times c, that's 4 minus 16, that's less than 0. So there are no roots that are real numbers for this, but it does mean I do have one point of discontinuity. So this has a domain from negative infinity up to, but not including, negative 2, and negative 2 up to infinity. That would be the domain. Okay. Decide whether the function is continuous. No. X cannot be equal to negative 2, right? That's where it says continuous. Horizontal and vertical asymptotes. Vertical asymptotes, well, we figured that one out. It's x equals negative 2. That's where we're dividing by 0, right? And it turns out that this doesn't actually go to negative 2 there. Horizontal. If we look at the highest powers here, they're both the same here at cubed. So the horizontal asymptote would be at y equals 4/3, right? And then if you verify this, it actually, well, it does all work out graphically. Okay, finding the zeros of rational functions. In this, find the zeros. This may not look like a rational function, but I would argue that this is the same as this, right? Minus negative, I don't know why they did that. But I can get a common denominator, because if I get a common denominator, because this is the same as 3x squared plus 6 plus 12 on the bottom, and by getting a common denominator, I get this as x squared plus 2. So now I've got 3x squared plus 18 over x squared plus 2. Don't try to cancel anything out. But are there any zeros? In other words, is 3x squared plus 18 ever equal to 0? At this point, we should be able to stop, because I'm never going to get this x squared to be equal to a negative. So this has no zeros, which means it doesn't cross the x-axis. If it was factorable or something like that, then we could actually solve it and find the zeros, but in this case it does not. Please note, this is kind of like a function divided by x squared plus 2, and this would be like the remainder, and I can combine that back together to get my original rational function. Say 44. Find the zeros, if any. Now, I'm going to go ahead and factor, because a lot of stuff they give us as factors. What times what is 5? Watch this. 2 times 5 plus 1 is 11, so that's one factorization. 3. Let's try this. 3. What if I did 3 times, I don't know. It's got to be a negative 10 and a positive 13, right? So what I'm trying to do is figure out if there's any sort of common factors here. So I know this is going to be a 3x and this is going to be an x. So what if I did 3 times, so 10 could be 2 and 5, right? So I could do 3 times 5, and I could make that positive, so that's a 15. And then that would have to be a 2, but it had to be negative minus 2. So that is it. The reason that's kind of important is because if you look, we have a removable discontinuity, which means that it does not count as a 0, right? Removable discontinuity at negative 5. The reason we had to factor it to check, but it does mean that the 0, there's only 1, is going to be negative 1/2. In other words, when is 2x plus 1 equal to 0? And that is it for section 2.6.